It's really fascinating that in building these systems that hundreds of millions of people use, you're rethinking about like how do you actually build it from first principles. So I should mention that versus primary design goals, it should be simple enough to learn as a first-time programmer, general enough for writing any kind of code and data, productive in the context of building, iterating, and shipping a project in a team setting, statically verified to catch as many categories of runtime problems as possible, compile time as we were talking about, performant for real-time open world multiplayer games. We didn't really quite talk about performance. Maybe I could ask you about that in a second. Complete so that every feature of the language supports programmer abstraction over that feature. Timeless, built for the needs of today and for foreseeable future needs. Yeah. And then there's some design goals that we talked about that is strongly typed. Multi-paradigm to use the best of functional programming, object-oriented programming, imperative programming. So it's as deterministic as possible. If you run it over and over, it runs in the exact same way. Failable expressions, as you talked about, is super fascinating. There's so many cool features in this. Speculative execution, concurrency. Maybe can you talk about concurrency? Like, what is it about verse that allows for concurrency at the scale that you need?
This is the one biggest technical problem that we're working to solve in this generation, and that is taming concurrency so that any ordinary programmer can achieve it by just writing ordinary code.
It's hard.
You know,
Yeah.
programming on a single-threaded computer is hard enough, but it is completely predictable. If you have a language that's deterministic and you run the same code over and over, it's always going to do exactly the same thing, and there's no unpredictability about what might happen, right? You're reading and writing variables in some order, and you're always going to see it behave the same. The problem is when you introduce multiple threads or multiple nodes in a data center all working together on a single problem, is that they each want to read and write different pieces of data and change the state of the world as they go. And still, almost all concurrency in real-world programs today is achieved manually. Uh, Programmers are writing this code that might run in multiple threads very, very carefully so that they are negotiating among each thread to get access to data in a way that's going to give them predictable results. Um, and it's incredibly hard. It's so hard that we've, in 5 generations of Unreal Engine, every single generation decided we're not going to try to scale up all of our gameplay code to multiple threads manually. It's just much, much, much too likely to go wrong, not only for ourselves, but for every partner company who licenses Unreal Engine and tries to use it for building a game. It's just a massive foot gun. There's a variety of solutions to concurrency that are all rather suboptimal. One attempted solution was like, just don't try to solve this problem at all. Let's break our program down into microservices. And almost all online websites of massive scale, like Amazon's.com, work with hundreds of microservices where different servers negotiate with each other by sending messages to each other. And by programmers writing those things very carefully, they eventually get to being able to take your orders and not make a mess of them reliably. Um, but this is totally not scalable to the metaverse where you have millions of programmers who are like mostly not going to be computer scientists. They're mostly going to be hobbyists and enthusiasts and first-time programmers doing stuff for fun. That's never going to work for them because they'll never be able to envision all of the different dependencies between different computations they're running in parallel. But it turns out that there was some amazing foundational work done in the 1980s that was made very real by a paper on Haskell concurrency. Composable memory transactions is the name of the paper. And it describes a system for transactional updates to programs. And the idea of a transaction is a block of code that does a bunch of operations on memory, might read, might write. It might process an order. It might accept an order or reject an order. If it might transfer money between one bank account and another. It might make conditional decisions like, oh, you asked to transfer $100 from your account to this guy's account. We're going to see if you have $100. If you don't, we're going to reject it. And if you have $100, we're going to take $100 out of your account and add it to this other guy's account. Without transactions, if everybody's just randomly adding and subtracting each other's bank balances, then you might have somebody read a bank balance, subtract 100, and write it out. But in the meantime, somebody has written something else in the meantime. And so you might get inconsistent bank balances arising if you don't have a way of ensuring that these all run in a specific order. So the idea of transactions is its way of dividing an entire program into updates uh, self-contained updates that do an arbitrary amount of computation, but must run in a single-threaded manner. And in the case of a game engine, that's a gameplay object update. When you're playing Fortnite, you see gameplay object. Every other player is a gameplay object. Every enemy is a gameplay object. Every rocket and projectile and car and thing you see moving around and interacting. It's not just a fixed static part of the world. That's a separate game object, and each of those objects is updated at you know a rate of one update per frame at 60 frames per second. And so then, in the course of Fortnite Battle Royale gameplay, you have tens of thousands of object updates happening every frame with 100 players. In a simulation with billions of players, you'd have a whole lot more than that.
So right now that's done single-threaded.
Yeah, that's done single-threadedly in each game session. This is why Fortnite is 100 players limitation. If you absolutely maxed out a server, maybe today you could get it up to 140 or something. But, it's not going to thousands or millions or billions. And so what we need is a technique for magically, automatically scaling our code to that. And transactions are the idea. And the idea is a transaction is a granule of code that runs its entirety. And so the idea of this transactional memory concept is that we're going to have programmers write completely ordinary code that reads and writes variables in the completely ordinary way, and they're not going to have to worry about concurrency at all. And then the system, like today, a computer just runs your program. There's no amount of speculation going on at the programming language level. The idea of transactions is, since we have a bunch of operations we need to know we apply a large set of them concurrently, but instead of each one reading and writing from global memory shared by all, in which case they might be reading and writing uh, and contending with each other for the same data and might be doing contradictory things to it, we're going to track all of our writes locally. We're not going to write we're not going to write changes out to global memory. We're going to keep track of it in a buffer that's just for that one transaction. So it's going to look to that code exactly as if it's running on the global system affecting global game state. But it's going to be isolated to just that one transaction, and it's going to be set aside and buffered up for consideration later. We're going to run tens or hundreds or thousands of these updates concurrently. We're going to see which ones had read-write conflicts. Because if two transactions don't read and write any of the same data, then you could have run them in either order or simultaneously, and it wouldn't have changed the end result.
Yeah, the order doesn't matter. I mean, this is so fascinating to imagine this kind of system and arbitrarily concurrent running millions of updates in parallel of gameplay objects. That's the thing that enables the thing that we're talking about, which is, tens of millions of people together in one scene.
Yeah, exactly. And the key is that you're running these updates speculatively, and you're not committing their changes to memory until you're sure that they're free of conflicts. So you might update 10,000 objects. You might find 9,000 of them were conflict free. So you apply those 9,000 updates to memory. And they could have run in any order, and it wouldn't have changed the result. Now there's
That's
1,000
so cool.
objects left over. Now you have to run those again, try them, maybe
Yeah.
interleave them in a different way to get them to eventually commit to memory. And in the meantime, you just throw all of their computations away and redo them later. And by doing this, like, we're moving this from being a programming problem for the programmer to deal with to being a language problem for us, the language designers, to deal
Mm.
with. And we're moving a vast amount of pain that would be imposed on a million people instead to a vast amount of pain imposed on a small number of people who have to actually make this work.
That's amazing. That's really incredible.